Imagine a star, much larger than our sun, nearing its end. It has burned through its fuel, fusing lighter elements into heavier ones for millions of years. Now, the core can no longer support its own weight. Gravity takes over, collapsing the core in a matter of seconds. This triggers a shockwave that rips through the star's outer layers, blasting them into space. This is a supernova, a cosmic explosion of unimaginable power. Supernova are the most powerful events in the universe. They shine brighter than entire galaxies for a brief period. The energy released in a single supernova explosion is more than the sun will produce in its entire lifetime. This makes them visible across vast cosmic distances, allowing astronomers to study the early universe. These stellar explosions are not just destructive events. They are also the universe's way of recycling elements. The extreme heat and pressure during a supernova create elements heavier than iron, such as gold, silver, and uranium. These elements are scattered into space, eventually becoming part of new stars, planets, and even life. Stars are born in giant clouds of gas and dust called nebulae. Gravity pulls these clouds together, causing them to spin and heat up. As the core temperature reaches millions of degrees, nuclear fusion begins. Hydrogen atoms fuse to form helium, releasing immense energy and creating outward pressure that balances the inward pull of gravity. This delicate balance between gravity and pressure defines a star's life. Smaller stars, like our sun, will eventually run out of hydrogen fuel and expand into red giants. They then shed their outer layers, leaving behind a dense core called a white dwarf. White dwarfs slowly cool down over billions of years, eventually fading away. However, massive stars, at least 8 times the mass of the sun, are destined for a more dramatic end. They burn through their fuel much faster, fusing heavier and heavier elements in their cores. When the core is mostly iron, fusion stops. Iron cannot be fused into heavier elements and release energy. The core collapses, triggering the supernova explosion. Supernovae play a crucial role in the evolution of galaxies and the universe. The shockwaves from these explosions compress nearby clouds of gas and dust. This triggers the formation of new stars, enriching the interstellar medium with heavy elements. Without supernovae, galaxies would be devoid of the elements necessary for planets and life. On Earth, we are literally made of star stuff. The calcium in our bones, the iron in our blood, and the oxygen we breathe were all forged in the cores of stars that exploded billions of years ago. Supernovae scattered these elements into space, where they eventually became part of the Earth and all life on it. Furthermore, supernova influence the structure of galaxies. The energy released by these explosions creates giant bubbles of hot gas that extend for thousands of light years. These bubbles can trigger star formation in some regions while suppressing it in others, shaping the distribution of stars and gas within galaxies. Despite our understanding of supernovae, many mysteries remain. Astronomers are constantly observing these events with increasingly powerful telescopes, trying to understand the details of these explosions. They are particularly interested in studying the neutrinos and gravitational waves emitted during supernovae. Neutrinos are tiny, almost massless particles that interact very weakly with matter. They are produced in huge numbers during a supernova and can provide valuable information about the core collapse. Gravitational waves, ripples in the fabric of space-time, are also generated during these events and offer a new way to study the dynamics of supernova explosions. By studying supernovae, we gain insights into the fundamental laws of physics, the evolution of stars, and the origins of the elements that make up our universe and ourselves. Each new observation brings us closer to unraveling the secrets of these spectacular cosmic events.